Okay, so today is the last lecture that we are going to have before your test, which is going to be on Friday. Tomorrow in class, we're going to go through the homework, and then we'll do some review stuff, and then Thursday will be some more review, and then you'll basically have your test. So the last thing that we need to talk about is assigning molecular polarity. And so the issue with molecular polarity is we've already talked about the fact that there are bonds that are polar and nonpolar and ionic, but a molecule itself can also be polar or nonpolar, and we'll talk about that in a second. So some things to consider is that when evaluating the polarity of an entire molecule, that is the whole thing, not just a bond, you have to consider the polarity of all of the bonds, the geometric arrangement, so the Vesper geometric shape of those bonds, and the impact of extra or unshared pairs of electrons on the center atom, and that's really key. The center atom is the really key part here. So we have two types of molecules. One is polar, and it has an uneven distribution of electrons in the molecule around the central atom, and the other is nonpolar, which is an even distribution of electrons in the molecule, again, around the central atom. And I'm sorry to disappoint, I brought the better technology home, so you will have a much better lecture instead of the one that was earlier this unit. Now, a couple of things to remind ourselves. So we have polar bonds. So polar bonds are an unequal sharing of electrons. And we have nonpolar bonds, which is considered to be an equal sharing of electrons. Okay, and then we have polar molecules, which are a lopsided electron distribution. And then we have nonpolar molecules, which are symmetrical electron distribution. Now I want to take a second to discuss what I mean by symmetrical or lopsided, because in biology you were told that if you cut something down the middle and it's mirror images on both sides, that would be considered symmetrical, and that's the truth, but it's not always the truth when we're talking about molecular polarity. We are talking about how the electrons are being distributed or represented around the central atom. So it can be symmetrical, but it might not be mirror images of each other. So let's work through a couple of examples. So we're going to assess NH3, which is the ammonia molecule, is polar and nonpolar. So the first thing that I recommend that we do is we draw the structure. So I have 1 nitrogen times 5 valence electrons, which will give me 5 valence electrons. I have 3 hydrogens times 1 valence electron, which will give me 3 valence electrons, and I'm going to add them up and find out that I have a grand total of 8 valence electrons. So the first thing I'm going to do is I'm going to draw my structure. So here's my nitrogen, put my hydrogens around, then I'm going to go ahead and create my bond. So I've used 2, 4, 6 shared pairs of electrons. Now I have 1 unshared pair or a lone pair of electrons on the central atom. So if we're going to go back and talk about shape here, which is important to remember or consider at the very least, I know that I have in I don't even know what letter that is. I have an AX3E1. AX3E1 would tell me that it is trigonal, pyramidal, Okay, so it's a trigonal pyramidal. And so what that tells me is that the shape of this particular molecule is roughly pyramidal. And we drew that, or I showed you an example of that yesterday in class. Now, the next thing that we have to do is we have to assess the types of bonds. So in this molecule, I have 3 nitrogen-hydrogen bonds. So the first thing I need to do is I need to assess whether or not the bonds themselves are polar. So between nitrogen and hydrogen, let's see. That's not what I wanted. So between nitrogen and hydrogen, nitrogen, 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 and hydrogen, 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 I know that the electronegativity difference of nitrogen, according to the periodic table, is 3.0, and hydrogen is 2.1, and that gives me electronegativity difference of 0.9. And so that tells me that each of the bonds represented here are polar bonds. So we have, let's see, we have a polar bond, polar, polar, and polar bond. Now, there's something that we need to talk about, and it's called a dipole moment. And so, well, let's back up a second. In the polar bonds for nitrogen, hydrogen, nitrogen, hydrogen, nitrogen, hydrogen, according to the electronegativity difference, where are the electrons going to spend most of their time? So the electrons, because nitrogen is the higher degree of electronegativity, the electrons are going to spend more of their time with nitrogen than they will with hydrogen. And so what that means is that they've created something special in chemistry that we call a dipole moment, or, well, a dipole. So it's a dipole, and I wish I could write that nicer because, yeah, even with better technology, guys, I still have terrible handwriting. So the dipole basically occurs in a bond that is polar and creates positive and negative sides to the bond. So, if I'm going to look at my nitrogen-hydrogen, I would say that because the electrons are spending more time with nitrogen than they are with hydrogen, that I would have a slightly positive side on my nitrogen and a slightly, nope, let me back that up. A slightly negative side on my hydrogen and a slightly positive side on my hydrogen. Wait, try that one more time. A slightly negative side on my nitrogen and a slightly positive side on my hydrogen. So that's going to occur for each of the bonds here. And so the way that we represent that in chemistry is, of course, we have a very special symbol for that. So we would represent that with the lowercase Greek letter D, or delta, which looks something like that, like a music note, and that's delta negative, and this side would be delta positive. And we'd have delta negative, and we'd have delta positive, and we would have delta negative, and we would have delta positive. Okay, so what that really is telling me is that in the individual bonds, the electrons are being pulled toward nitrogen consistently. And as a result of that, we're going to draw this really special funky arrow, which has a plus on the tail of it, and the plus is the positive side of that particular bond, and then the arrow is pointing to the negative side. So in this particular case, the molecule has a positive side, and all of the bonds have a positive side and a negative side. And because the bonds are polar, this molecule appears to also be polar. Well, but the issue is that it is definitely polar, but not because of the bonds necessarily. It's polar because the electrons are centered more around the central atom than they are around the outside atoms. So if you think about it like in terms of a pyramid, if you think about it in terms of a pyramid, which is what this particular molecule is, right? If this is my central atom up here, all of the electrons are being pulled up and towards the central atom. So that makes that this molecule is actually lopsided. So the whole molecule has something that we call a dipole moment. Because all the electrons are being pulled toward the central atom. Gee, that's not even a word. And so we would represent the whole molecule would have a dipole with an arrow like that. Now, one last thing I need to say about this particular molecule. Molecules that tend to have unshared pairs of electrons are almost always polar. And that's because those electrons are creating an electron density right around the central atom. All right, so let's another example without all of the things. So first thing first, we're going to draw the molecule. So I have one carbon atom times 4 valence electrons, which would give me 4 valence electrons. I have 4 hydrogen atoms times 1 valence electron, which is 4 valence electrons. And when I add all of that business up, I get 8 valence electrons. Okay, so I'm going to draw this with my central atom. So carbon in the middle, my hydrogen spread out equally, and I'm going to create a bond, and so that's 2, 4, 6, 8. That's 8 electrons that I've used. It's 8 electrons that I had. So now I need to assess a couple of things. So I know that I have carbon, nope, wrong one. Carbon, and hydrogen. I have 4 bonds. Ooh. Oh, I don't even know what happened there. Geez. Okay, so I've got 4 bonds, and when I assess the electronegativity difference, I have 2.5 minus 2.1, which gives me an electronegativity difference of 0.4. So that tells me that my bonds, all of my bonds, are nonpolar. Okay, so all my bonds are nonpolar. And because all of my bonds are nonpolar, that tells me that the electrons are being shared equally. Oh boy. And as a result of that, this molecule ends up not having any dipole moments. So the electrons are not spending any more time with one atom than they are with another atom. And so as a result of that, we would say that this molecule is symmetrical. And if the molecule is symmetrical, we would call it a nonpolar molecule. So in this case, the molecule has all nonpolar bonds and is a nonpolar molecule. Okay, so let's take a look at another example here. So we have ASH3. So the first thing we're going to do here is we're going to draw, or we're going to assess what we've got. So AS, I've got one of those, times the fact that it has 5 valence electrons, and I have 3 H's, 3 H's times 1 valence electron, so that's 3 valence electrons, so another grand total of 8 valence electrons. So first going to draw my atom, so it's AS, and I have H, 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 2, 4, 6. I have 2 more electrons to place. I'm going to put those lone pairs on the central atom. I'm going to check my bonds here. So in this case, I have 3 ASH bonds. And when I go to check my electronegativity difference, arsenic is 2.0, hydrogen is 2.1, which gives me an electronegativity difference of 0.1. So that tells me that these are all nonpolar bonds. So those are all nonpolar bonds. And the issue is that because they're all nonpolar, the electrons are being shared equally. So let's consider that. So all bonds are nonpolar, and the electrons in those bonds are being shared equally. Okay, so on first glance, we might consider this molecule to be a nonpolar molecule, but the problem, well, not the problem, but the issue is that we have these 2 unshared pairs of electrons right here. Those 2 unshared pairs of electrons are creating a lopsided electron density around the central atom. So even though the electrons that are being shared between the arsenic and the hydrogen are being shared equally, those 2 unshared pairs of electrons on the central atom make this molecule become lopsided. So the molecule is lopsided. Okay. So remember that the molecule has nonpolar bonds, but because of the unshared pairs of electrons on the central atom, the molecule becomes polar. So the molecule is lopsided even though it has all nonpolar bonds. The unshared pairs of electrons on the central atom make it polar. Okay, so that's what ends up happening there, and that's a really important distinction to understand. Now, last one, before I go through a summary or so, is that we need to assess whether the CF4 carbon tetrafluoride molecule is polar or nonpolar. So just like we've done with the other ones, I'm going to say that I've got 1 carbon times 4 valence electrons, and I have 4 fluorines times 7 valence electrons, which is 28. And when I add all of that business up, I get 32 valence electrons. So when I go to draw this structure, I'm going to take my carbon, put it in the middle. I'm going to take my fluorines and place them around the carbon. I'm going to bond them together. And then I'm going to go ahead, 2, 4, 6, 8, and I'm going to go ahead and fill in the rest of the electrons. So that's 6, 12, that's 6, not 6, that's silly. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. We're good. We've drawn the entire structure, so that's fantastic. Now, first thing I want to note here is that we have carbon and fluorine bonds, and we've got 4 of them. So we've got carbon, 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 and fluorine, 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 fluorine. They're all bonded together, and when I go to assess their electronegativity difference, I get a 2.5 minus 4.0, which gives me a value of 1.5, which makes all of these bonds polar. Okay, now here's the thing. All these bonds are polar, but where is the electron going to spend most of its time? Well, the electron is going to spend most of its time on the fluorine side of the bond. Okay, and so it's going to create a dipole in between the carbon and the fluorine, but the dipole is going to be pulled out towards the fluorine. So when we go to represent that, we would have delta negative, delta positive, delta negative, delta positive, delta negative, delta positive, delta negative, delta negative, delta positive. So that says that all of these bonds are having electrons that are spending more time away from the central atom than with the central atom. And they're being pulled with the exact same amount of pull in opposite directions. And because they're being pulled with the exact same amount of pull in opposite directions, the idea or the core or the idea is that the electrons density around the central atom is actually symmetrical because they're being pulled away evenly. So what I'm getting at here is that even though this molecule has polar bonds, the molecule is still symmetrical. So there is no dipole moment. So this molecule is non-polar. Okay, so it's not too bad, but there's just some things that we need to consider. Now, this molecule, we forgot to identify it. Silly us. This is an AX4, which makes it tetrahedral. Okay, and now I'm going to show you a really, really quick example of a tetrahedral molecule. Oh boy, let's see here. I need to add. Nope. Oh boy. Oh boy. Edit. No. Oh boy. I want to add another slide here. How do we? Oh, that's how I do it. Okay. No. Uh-oh. Ruh-roh. Oh, did I just say that? Oh, hold on. Hang on. Okay, sorry about that. So, the next molecule I want to draw for you is one that has more than one type of atom. I'm sorry, more than 2 types of atoms. So I'm going to have, this molecule is going to be Cl2H2. So in this case, I have my central atom, which is chlorine, or carbon rather, and I have 2 chlorines times 7 valence electrons, which is 14 valence electrons, and then I'm going to have my hydrogen, which is 2 hydrogens times 2 valence electrons, which is 2 valence electrons, and then 4 valence electrons, and then we add all of that business up, and we end up with something like 20 valence electrons. So now I'm going to take and draw the structure, which is carbon, and chlorine, and let's see, chlorine, and hydrogen, and hydrogen, and I'm going to now bond them together, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Okay, now in this case, I've got a lot of bonds to take a look at. So I've got the carbon, 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 hydrogen bonds, and the chlorine bonds. So in this instance, the electronegativity difference between carbon and hydrogen is, let's see, it's 2.1 minus 2.1. So that tells me that this is a 0.0. Oh boy, 0.0. So these are both nonpolar. Okay, and then down here I've got a 2.1 minus chlorine, which is a 3.0, which gives me a 0.5, and that gives me polar. So I have a structure here that has 2 nonpolar bonds and 2 polar bonds as part of it. And so I have a dipole, where I have a situation where the electrons are going to spend more time with chlorine in 2 bonds, and in the other 2 bonds they're going to be shared equally. So in this case here, I'm going to have a negative and a delta positive, and a negative and a delta positive, and so the electrons are going to spend more time going towards the chlorine than they are going to spend towards the carbon. And so as a result of that, this entire molecule has a dipole moment shifting this way. So this becomes a very lopsided molecule. Because it has both polar bonds and nonpolar bonds around the central atom. Okay. So the molecule itself is polar. Okay. Now, just a couple of things to help keep track of some stuff here. So, a summary of bond polarity. Okay. First thing is we need to look at electronegativity differences. In all of the bonds present around the central atom. We also need to look at the presence, or look for the presence of unshared pairs of electrons on the central atom and then lastly we need to look at the molecule for symmetry or lopsidedness. If that's even a word. Okay, so your homework is to complete the next page in the packet, which I believe is assigning molecular polarity. I think it's worksheet 5 or 6. I believe it's a two-sider, and we will go through that in class tomorrow. Good luck.